Welcome, everyone. Today, I am pleased to introduce the Hybrid TUI Architecture, a paradigm shift in how we approach high-performance terminal user interface engineering. By synergizing Zig and SolidJS within the OpenTUI and OpenCode ecosystem, we have created a system that balances developer productivity with raw execution speed. As illustrated, our architecture bifurcates responsibilities. SolidJS serves as the robust engine for application logic and reactive state management, while Zig handles the heavy lifting of the rendering layer. This strategic integration allows us to leverage modern reactive patterns while maintaining the low-level efficiency required for the most demanding terminal environments. When we approach a TUI as a game engine, we encounter a specific engineering constraint. Modern terminals are capable of 60 FPS streams, but the overhead of a traditional virtual DOM creates significant bottlenecks. This manifests in two primary ways: full tree reconciliations that trigger garbage collection pauses, and clear scrollback operations that cause visual flickering. Looking at the performance comparison, the graph for traditional VDOM cycles shows high variability and frequent GC pauses. This is typical of a competitor stack using Node, React, and Ink, which demands a memory footprint between 360 and 746 megabytes of RAM. In contrast, the approach used by OpenCode, leveraging Zig and Solid, utilizes signal updates. This produces a stable stream with minimal overhead, as shown in the second graph. This efficiency translates to a much lower memory footprint of approximately 130 megabytes, ensuring smooth performance even under high-frequency update requirements. The solution we have implemented is a hybrid sandwich architecture, a three-tier model designed to maximize both developer productivity and system performance. At the top, the logic layer uses TypeScript and SolidJS to handle state management and UI definitions, providing a robust environment for building complex features. Below this, the bridge utilizes Bun's high-speed foreign function interface to facilitate near-instant communication between our high-level code and the underlying system. At the base of the stack is the metal, where Zig native executes performance-critical tasks like rendering, buffering, and ANSI parsing. By offloading these intensive operations to a low-level language while maintaining a modern front-end stack, we achieve a highly responsive user experience without compromising on code maintainability. Moving into the logic layer, let's examine the role of fine-grained reactivity and why SolidJS is central to our approach. SolidJS distinguishes itself by utilizing signals rather than a virtual DOM, which allows for a high degree of architectural precision. The key integration benefit here is the ability to perform direct updates to text nodes, bypassing the need for computationally expensive tree diffing. Looking at the diagram, the signal update targets only the specific node that requires a change, highlighted in green, while the surrounding nodes, marked with an X, remain completely unaffected. To achieve this, our implementation leverages a custom reconciler at OpenTUI/Solid, which efficiently translates signals into direct render operations. The render layer leverages the Zig programming language to deliver native performance. Its primary responsibilities include the intensive parsing of ANSI escape sequences found in the ANSI.zig source file and the management of frame buffering. From a performance perspective, Zig compiles directly to native machine code, allowing us to consistently hit our 16-millisecond frame budget for a fluid 60 frames per second. By utilizing manual memory management with packed structs, we ensure zero overhead and avoid the unpredictable pauses associated with garbage collection. This architecture illustrates how Bun's foreign function interface serves as a high-performance bridge between high-level logic and low-level execution. On the left, SolidJS operates within the JavaScript and TypeScript environment to calculate state changes. Rather than relying on traditional JSON serialization, which often introduces significant overhead, this system utilizes Bun FFI to pass binary data directly through the pipeline. On the receiving end, the Zig binary directly updates the memory buffer, ensuring a seamless, low-latency transition from front-end reactive logic to native performance. The render loop lifecycle is divided into 5 critical stages designed for maximum performance. It begins with the input phase, where a user action or an AI token triggers a signal update. In the second stage, reconciliation, the @OpenTUI solid library catches this update to determine the necessary changes. Next, the handoff occurs through a Bun FFI transfer, moving data quickly into the lower-level processing layer. The fourth stage leverages Zig for smart diffing, which identifies the precise delta between frames to minimize work. Finally, the output is delivered as minimal ANSI codes to std out. This entire sequence is engineered to execute in under 16 milliseconds, maintaining a seamless 60 frames per second interface. To eliminate flicker during terminal rendering, Zig utilizes a technique called double buffering. Traditionally, a terminal application might issue a clear command before drawing the next frame, which often causes a noticeable flash or flicker. Instead, Zig maintains two distinct buffers: Buffer A, which represents the current screen state, and Buffer B, which contains the next state intended for display. By calculating the difference, or diff, between these two buffers, the system identifies only the specific characters that have changed. As shown here, while the word hello remains the same, the word world is replaced by Zig. Only these changed characters are written to the terminal, ensuring a smooth transition and a much more stable user interface. Our memory management strategy addresses a fundamental efficiency problem found in standard JavaScript-based terminal user interfaces. Typically, these TUIs rely on heavy JavaScript objects for every individual UI element, which leads to significant bloat within the V8 heap. To solve this, we leverage Zig's packed structs to provide a much more compact and efficient data representation. This transition results in a drastic reduction in heap usage and minimizes the overhead associated with JavaScript closures. As shown in the comparative data for idle memory usage, a Node and React-based implementation like Claude Code requires 360 megabytes, whereas our Zig and Solid-based OpenCode architecture consumes only 130 megabytes. This nearly threefold reduction in resource consumption ensures that the interface remains lightweight and responsive without sacrificing functionality. Moving beyond text, we are focused on native animation and 3D capabilities. Our timeline engine is managed by src/animation/timeline.ts and maps execution directly to the native layer to ensure maximum smoothness during playback. Looking at our future roadmap, we are integrating WebGPU for hardware-accelerated 3D rendering inside the terminal. This implementation is located in src/3d/wgpurenderer.ts. As demonstrated by the native rendered element on the right, these advancements allow us to bring sophisticated visual depth to what was previously a text-only environment. In our case study on low-latency input handling, we address the common challenge of typing lag caused by Node.js event loop blocking. To overcome this, we implemented a Zig-based solution that interacts directly with the raw stdin stream. By parsing ANSI escape codes natively, the system efficiently filters out input noise and dispatches only clean, high-priority events to the SolidJS frontend. This low-level approach significantly reduces latency and enables the reliable use of complex key courts, such as Ctrl plus Shift plus Enter, ensuring a responsive and seamless user experience. We are focused on achieving the optimal balance between developer experience and user experience. On the left side of the scale, we leverage TypeScript and SolidJS. This provides an exceptional DX, allowing developers to write declarative UI through what we call vibe coding, making the development process both intuitive and efficient. On the right side, we prioritize the user experience by integrating Zig. By doing so, we deliver compiled native performance, or metal speed, directly to the end user. This architecture ensures that a high-quality developer workflow translates into a lightning-fast application for our users. Our roadmap for polyglot integration begins with the development of Go bindings, specifically located within the packages/go/OpenTUI.go directory. This provides the necessary foundation for interfacing with Go-based logic. Next, we are implementing a native frame buffer to significantly reduce JS native traffic, which is a critical step for optimizing communication and rendering performance. Following this, we will introduce virtual lists to facilitate high-performance logging, ensuring the system can handle large volumes of data efficiently. Throughout these stages, the Zig rendering layer remains entirely agnostic to the front-end logic, allowing for a flexible and modular architecture across different programming environments. Let's examine the core technical benefits of this architecture. To eliminate visual stutter, we utilize Zig-based double buffering and diffing, ensuring a zero-flicker experience. To achieve industry-leading low latency, we have integrated SolidJS signals with Bun's foreign function interface. We also significantly reduce the memory footprint by utilizing Zig structs as a direct replacement for high-overhead JavaScript objects. Finally, we offer a modern developer experience by leveraging reactive programming patterns without the traditional performance costs of a virtual DOM. OpenTUI introduces a hybrid architecture specifically engineered for the next generation of command-line interface tools. By combining the declarative ease of React with the high-performance execution of Metal, we provide a robust framework for building modern terminal applications. Our approach ensures that developers no longer have to sacrifice performance for productivity, delivering a seamless and highly responsive user experience directly at the command line.